The Milky Way has already collided with other galaxies, and it's set to happen again, suggesting our cosmic home is built from wreckage, not pristine creation. Lily, this immediately challenges our perception of a stable, unchanging galaxy, doesn't it?
It absolutely does, James. We tend to think of the Milky Way as this serene, isolated spiral, but the truth is far more dynamic. Over billions of years, it's been an active participant in what you could call cosmic cannibalism, absorbing countless smaller galaxies. Imagine these as faint, luminous companions that drifted too close, got caught in our galaxy's gravitational embrace, and were slowly dismantled.
So it's not just a theoretical past event. This process of absorption is happening right now.
Precisely. Take the Sagittarius dwarf galaxy, for instance. Even as we speak, it's in the process of being pulled apart. Its stars scattered into long, winding tidal streams that wrap around our own galactic disk. It's a live demonstration of how galaxies evolve, not in isolation, but through these gravitational interactions.
And the ultimate collision, the one with Andromeda, is still billions of years away, but it's a certainty. What will that look like? Will it be a violent, destructive impact?
It will be a collision, but not in the way our human minds might imagine. Stars are incredibly far apart, so the chances of two individual stars actually hitting each other are infinitesimally small. Instead, it will be a grand, slow-motion gravitational dance. The two great spirals, the Milky Way and Andromeda, will warp and stretch each other, creating vast arcing tidal tails. Our central black holes might eventually spiral together, and over billions of years, the two galaxies will merge into a single, much larger system. It's a slow, elegant, and ultimately transformative event.
So the new galaxy won't be a classic spiral anymore.
Most likely not. It will fold into a new form, vast and quiet. This cosmic evolution, this merging and reshaping, shows us that even galaxies aren't eternal in a static sense. They are constantly changing, colliding, and beginning again.
It's a profound thought that our home is made from the wreckage of others. But even more mind-boggling is the claim that some stars in the Milky Way are actually older than the Milky Way itself. How is that even possible?
It sounds paradoxical, doesn't it? But it's true. Not every star we see in our galaxy was born here. We're talking about a population of stars known as halo stars. These are ancient, very poor in heavy elements, and they wander in long, tilted orbits high above the galactic plane. Astronomers believe these stars originated in smaller, primordial galaxies, which then merged with the Milky Way billions of years ago.
So they're essentially refugees from other smaller systems that were consumed by our galaxy.
Exactly. Their chemical fingerprints are key here. They show almost no heavy elements, indicating they formed very shortly after the Big Bang, before the universe had much time to produce those elements. They're like living fossils, giving us a glimpse into a much younger, wilder universe, still forming its first structures.
It's like finding ancient spirits from a time before order, before the spirals we recognize now. What do these stars tell us about the early cosmos?
They're invaluable. Because they are so metal-poor, they essentially preserve the chemical conditions of that early epoch. By analyzing their composition, we can peer back into the period just after the Big Bang, before galaxies had matured, and before the Milky Way had fully taken shape. They are literally fossils made of light, allowing us to understand what the universe was like when it was still learning to become what it is today.
That's a powerful image. And while these ancient stars drift, our own solar system is on its own incredible journey. We orbit the center of the Milky Way at an astounding speed, over 828,000 kilometers per hour. That's more than 230 kilometers every second. Yet, it takes 225 million years to complete just one loop around the galaxy. This galactic year really puts our human timescales into perspective.
It's a staggering thought. In Earth time, our solar system has only completed about 20 orbits around the Milky Way since it formed. To give you an idea, when the first dinosaurs appeared, we were in a completely different part of the galaxy. Everything is in motion, constantly, endlessly. Even as we rest, the Earth turns, the Moon circles, and our entire solar system sweeps forward through a galaxy in motion.
It makes you realize how fleeting our position in space truly is. The stars we see today weren't always nearby and won't always remain. And this motion isn't just internal. The galaxy itself is still growing.
Yes, despite its immense age, the Milky Way isn't a finished product. It's constantly gathering material. This comes from various sources: gas from the intergalactic medium, stars from captured dwarf galaxies, and even streams of dark matter that feed its halo. It's a slow gravitational deepening rather than growth in a biological sense.
So it's not expanding like a balloon, but rather accumulating mass and growing more complex.
Precisely. Some of this growth is quiet, like in falling clouds of gas, but other times it comes with significant disruption, as satellite galaxies are torn apart and their stars are scattered across the sky. The Milky Way you inhabit today is fundamentally different from the one the dinosaurs saw, and your distant descendants could know a galaxy larger still, stitched together from the ruins of 1,000 smaller worlds.
It's a galaxy that's never static, always in flux. Given this dynamic nature, it's perhaps less surprising that we don't even know how many arms the Milky Way has. That seems like a fundamental detail, yet it remains a mystery.
It's surprisingly difficult to map from our vantage point. We're situated deep inside the disk, surrounded by dust clouds that obscure distant regions. Stars blur into one another, making it incredibly hard to get a clear overall picture. For decades, astronomers believed there were 4 major spiral arms. More recent observations, however, suggest there might be fewer, or that the arms twist and split in ways far more complex than we initially imagined.
So the neat pinwheel image we often see in illustrations isn't quite accurate.
Not necessarily. Some arms fade into fragments, others wrap unexpectedly. The Milky Way might not be a perfectly neat pinwheel at all, but a living, layered swirl of stars shaped by forces we still don't fully understand. Our internal perspective really limits what we can directly observe.
It's like being inside a forest and trying to map the entire forest. And within this complex, swirling structure, there are individual stars that are flung from the core, traveling at astonishing speeds. These rogue stars sound like a violent exception to the galaxy's gravitational-bound nature.
They absolutely are. While most stars drift calmly, a rare few are hurled outward at speeds fast enough to escape the Milky Way entirely. These are called hypervelocity stars. One of the main mechanisms for their creation is interactions with the supermassive black hole at the center of our galaxy.
The central black hole, Sagittarius A.
Precisely. If a binary star system, 2 stars orbiting each other, gets too close to Sagittarius A, the black hole's immense gravity can disrupt that system. One star might fall into the black hole and vanish, while its companion is gravitationally slingshot outward, hurled into the dark at over 1,000,000 kilometers per hour. These rogue stars travel alone, far from the galactic plane, like glowing comets with no return.
It's a stark reminder that even within a galaxy bound by gravity, there are moments of violent release, quiet expulsions sending stars flying into intergalactic night. And speaking of cosmic events, we've touched on the Andromeda collision, but it's such a monumental future event, it's worth revisiting. That faint blur we see in the night sky is literally hurtling toward us.
Yes, that faint blur, the Andromeda galaxy, lies over 2 million light-years away, and yet it's moving steadily toward us. In about 4.5 billion years, our 2 great spirals will collide. As we discussed, it won't be stars smashing into each other, but rather a slow, elegant dance of gravitational forces.
So the new galaxy will be a different shape. Will our solar system survive intact?
The solar system is highly likely to remain intact, though our view of the night sky would be radically transformed. The position of our sun within the merged galaxy could change dramatically, perhaps moving into a different orbit entirely. The gravitational pulls will warp both galaxies into long, stretching arcs, and the central black holes could eventually merge, but our small planetary system is robust enough to endure the larger cosmic shuffle.
It gives a new meaning to cosmic dance. And another intriguing anomaly within the Milky Way is that some stars orbit backward, moving in retrograde. How does a star end up moving against the galactic current?
Most stars in the Milky Way orbit the center in the same general direction, but these exceptions are fascinating. These retrograde stars, especially those in the outer halo, orbit opposite to the galaxy's main rotation. Their reversed motion is a clear signature of their foreign origin. They almost certainly arrived from elsewhere, born in dwarf galaxies that were later absorbed by the Milky Way.
So the galaxy literally carries old memories in its motion, stories of ancient mergers preserved in the turning of stars against the stream.
Exactly. They are like cosmic immigrants whose motion tells us about the Milky Way's tumultuous past, reminding us that our galaxy is a composite, not a pristine spiral. The chemical makeup of stars further reinforces this idea, revealing their origin. Every star, in a way, carries a unique chemical fingerprint.
How does that fingerprint work? What tells us where a star came from?
It's all about the elements. By studying the patterns of elements imprinted at birth, astronomers can trace a star's history. Some stars are rich in heavy elements like iron and calcium, suggesting they formed in dense, metal-rich regions. These elements were forged in previous generations of stars, meaning those stars are relatively younger. Others, the metal-poor stars we discussed earlier, are nearly pure hydrogen and helium, signifying they were born when the universe was still very young.
So chemistry becomes a kind of time machine, letting us read a star's past like an ancient poem written in light.
That's a beautiful way to put it, James. These differences allow scientists to group stars into families, uncover ancient mergers, and reconstruct the hidden story of the Milky Way's formation. It's how we piece together the history of a galaxy that's accumulated stars from potentially dozens of smaller dwarf galaxies over billions of years.
And the remnants of these consumed galaxies often leave behind vast, ghostly trails across the sky, known as stellar streams.
Indeed, these are thin ribbons of stars stretching in arcs and curves, barely visible to the naked eye, but unmistakable when mapped with precision. They are the leftovers of smaller galaxies that wandered too close to the Milky Way and were literally pulled apart by tidal forces. As they orbit, their stars are smeared across space, forming these long, delicate trails that trace their former paths.
It's a powerful visual, the galaxy carrying the rings of its past in every thread of light. And these interactions don't just create stellar streams, they also cause the entire Milky Way to warp.
That's right. Our galaxy isn't a perfectly flat disk. It bends upward on one side and downward on the other, forming a graceful wave across the stars. This subtle warp was initially invisible to us until radio telescopes mapped the hydrogen gas that stretches far beyond the starlight of the main disk.
What causes this distortion?
Astronomers believe it may be caused by satellite galaxies, like the Magellanic Clouds, tugging gently on the Milky Way's edges, or by the gravitational influence of clumps of dark matter bending the structure from below. It shows that, like ripples in a great spinning sheet, even galaxies are never fully still. They bend, flex, and change form in response to invisible forces.
So, from a distance, the Milky Way might actually look like it's dancing slowly through space. It also puts into perspective how little of this vast structure we can actually perceive. The fact that we can only see about 0.0003% of the Milky Way with the naked eye is quite sobering.
It really is. Under a clear, dark sky, far from city lights, you might see a few thousand stars, which feels like an ocean of light. But that's barely a droplet compared to the over 100 billion stars the Milky Way actually contains. Most are hidden from view, either behind thick curtains of dust, or simply too faint or too far away for our vision to reach.
So the pale streak of the Milky Way that crosses the sky on moonless nights is just the innermost whisper of the whole.
Exactly. We live surrounded by a colossal river of starlight, and yet almost all of it remains invisible to us, simply too vast to grasp from within. This internal perspective also means that stars within the galaxy don't all move uniformly. They orbit at different speeds.
Unlike planets in a solar system where the inner planets move faster, how does that translate to a galaxy?
It's a crucial difference. Some stars race ahead in the inner regions, while others drift slowly along the outskirts. This difference in speed is why spiral arms aren't solid, static structures. They're patterns like slow traffic jams of stars and gas moving through space. As these density waves pass, they compress gas and trigger new stars to form, lighting up the arms in curls of blue and white.
So the galaxy isn't a clock, but a current, and we're drifting in it.
A perfect analogy. Our own sun is part of this swirl, moving in and out of these patterns across cosmic time. But this differential rotation also brings us to one of the galaxy's greatest mysteries. It holds together because of something we cannot see. By all logic, the Milky Way shouldn't exist as it does.
What do you mean it shouldn't exist?
Based on what we can measure, the visible stars, dust, and gas, the outer edges of the galaxy are spinning too fast. They should be flung into space, scattered like leaves in a storm, and yet they remain bound. The answer, astronomers believe, is dark matter.
The invisible scaffolding.
Precisely. This mysterious substance doesn't shine, reflect, or emit any light, so we can't see it directly. But it exerts gravity, and there's so much of it that it outweighs all the visible matter in the galaxy many times over. Without it, the Milky Way would indeed fly apart. We don't know what dark matter is, but we know that without it, the Milky Way wouldn't hold together.
It's an elegant solution to a profound problem, even if it introduces another layer of mystery. And at the very heart of this dark matter-bound galaxy, there's the supermassive black hole, Sagittarius A.
Indeed. At the core, Sagittarius A is an enormous black hole, more than 4 million times the mass of our Sun, yet it occupies a space smaller than the orbit of Mercury. We can't see it directly, but we've observed nearby stars whipping around it at tremendous speeds, tracing invisible loops through the void. Occasionally, gas and dust fall inward, flaring with X-rays as they spiral into the event horizon.
Is it always as quiet as it seems now?
For now, Sagittarius A is relatively dormant, but long ago it may have burned like a quasar, lighting up the galaxy from within with intense radiation. It's the silent conductor of the Milky Way's heart, pulling stars into a slow, relentless dance.
And the central region itself isn't a simple sphere. Astronomers discovered the Milky Way has a peanut-shaped bulge.
That's correct. When astronomers mapped the center, they found the bulge wasn't a smooth, round ball of stars, but a three-dimensional peanut shape. From the side, it swells in the middle and narrows at the ends, almost like a twisting hourglass made of stars. This strange geometry likely formed from the galaxy's central bar, a dense stripe of stars that rotates slowly, buckling and puffing upward over time.
So our spiral galaxy's heart is full of more complexity than we might imagine, not flat or clean, but intricate and alive. This complexity extends to the spiral arms themselves, which are actually shaped by stellar nurseries.
Yes, the spiral arms aren't just collections of stars. They are, in essence, woven from the birthplaces of stars. Giant clouds of hydrogen, dust, and molecules drift through the galaxy, and when these clouds pass through the spiral arms, they are compressed. This compression triggers them to ignite with newborn suns. These regions are what we call stellar nurseries, chaotic, glowing, and full of motion.
So the blue and white curls we see are bursts of creation.
Exactly. Ultraviolet light from these new stars illuminates the clouds, painting the arms with radiant blues and silvers. These bursts of creation trace out the spiral shape, illuminating the curves of the galaxy with quiet fire. Every star, including our own sun, was born from one of these cloudy cradles long ago.
And encircling this entire dynamic, complex disk is a vast halo.
Beyond the flat spiral disk, there's a much more diffuse spherical halo that surrounds the entire galaxy. Though nearly invisible, this halo contains ancient stars, globular clusters, and enormous amounts of dark matter, potentially holding the majority of the Milky Way's mass. Its stars are spread thinly across vast distances, orbiting in long, slow arcs that rarely touch the disk.
It sounds like the galaxy's outer memory.
A good way to describe it, it preserves the remnants of ancient galactic mergers, streams and shells of stars torn from smaller galaxies. It's quiet and dim, but still in motion, still shaping what the Milky Way becomes. Within this halo, we find over 150 globular clusters.
These are incredibly old, tightly bound spheres of stars, aren't they?
AR. Globular clusters are among the oldest objects in the galaxy, some more than 12 billion years old, containing hundreds of thousands of tightly bound stars. They orbit the galactic center in the halo like moths circling a distant flame. Their stars are metal poor, meaning they formed before the universe had time to create many of the heavier elements.
So they're like time capsules holding clues to the galaxy's early formation.
Exactly. They tell us about the conditions in the early cosmos and what the galaxy consumed. These quiet, golden spheres drift patiently above and below the galactic plane, glowing in the dark, acting as silent witnesses to the galaxy's infancy. And all this while the galaxy continues its growth, accumulating material.
Yes, we've discussed that it's an ongoing process of gathering gas and stars. What does that mean for the galaxy's long-term future, beyond the Andromeda collision?
It means the Milky Way is in a constant state of transformation. Even after the Andromeda merger, the new galaxy will continue to interact with its environment, drawing in more gas from the intergalactic medium and potentially encountering other galaxies in its larger cosmic neighborhood. Its future shape and composition are still being written, influenced by both internal dynamics and external forces.
And within this evolving system, we again see these rogue stars flung from the core. Are there other mechanisms besides the supermassive black hole that could create these hypervelocity stars?
While the supermassive black hole is a primary culprit, other scenarios can also produce hypervelocity stars. For instance, supernova in binary systems where one star explodes can kick its companion out at extreme speeds. Also, close three-body encounters in very dense star clusters can gravitationally slingshot a star out of the system. So it's not just the core's black hole at play, but other violent gravitational interactions throughout the galaxy.
It highlights how a galaxy is a place of both slow, majestic change and sudden, explosive violence. Given all this activity, it's perhaps not surprising that star formation in the Milky Way appears to be slowing down.
That's a key observation. Long ago, the Milky Way was far more active, bursting with fresh stars forming from dense, collapsing clouds. But in recent epochs, the pace has indeed slowed. There's still gas available, but much of it is now spread thin, heated, or locked in forms that resist collapse.
So the galaxy is not done making stars, but it's entering a quieter phase.
Exactly. Astronomers estimate that star formation peaked billions of years ago and has been declining ever since. This doesn't signal an imminent end, but rather that we are living in a more mature, quieter chapter of the galaxy's life. It's still forming stars, but no longer in such a hurry, glowing gently in its middle age.
And before the galaxy even settled into this mature phase, before it even had a distinct disk, some stars were already forming. What does that tell us about the very early stages of the Milky Way?
It tells us that the disk, the broad, flat spiral we associate with the Milky Way, formed gradually over time. These ancient stars reside mostly in the halo, or the thick disk, and they formed when the galaxy was still assembling, more of a loose cloud of gas, stars, and dark matter slowly collapsing inward. By studying their composition and motion, astronomers can peer back into the era before this structured disk, before the elegant spirals we see today.
These stars are truly the elders of the galaxy, silent witnesses to its birth and the long, slow shaping of what we now call home. Revisiting the concept of the galactic year, the fact that it takes 225 to 250 million Earth years for our Sun to complete one orbit is a powerful reminder of cosmic timescales.
It is. In the time it takes for the Sun to circle the galaxy once, continents drift, species rise and fall, and entire epochs unfold here on Earth. It's thought that we're currently about halfway through one such orbit. The last time our solar system was in this part of its path, the supercontinent Pangaea had just begun to break apart, and dinosaurs had not yet emerged. It's the slow, steady heartbeat of cosmic time.
And in its entire 4.6 billion-year existence, our Sun has completed fewer than 25 galactic orbits. That seems remarkably few given its incredible speed.
It's because the galaxy is simply so vast, and the Sun's path so long, that each orbit takes hundreds of millions of years. We often think of stars as ancient and unmoving, but our solar system is still relatively young on a galactic scale, a newcomer in a city of older, more traveled suns. We are part of the galaxy's motion, but still early in its long, winding story.
And this leads us back to the rotation curve, where the Milky Way's rotation defies Newton's predictions. That outer stars orbit almost as quickly as inner ones is a direct contradiction of classical physics.
Exactly. According to Newtonian physics, stars farther from the galactic center should orbit more slowly, just as outer planets move more leisurely around the sun. But in the Milky Way, that's not what we observe. The reason, as we discussed, is dark matter. It's an invisible, unknown form of mass that surrounds the galaxy in a vast halo.
So without dark matter, the galaxy wouldn't hold together.
That's the current consensus. With dark matter, the math works, explaining the observed rotation speeds. The Milky Way effectively turns like a solid wheel, not because we understand it fully, but because something unseen is holding it in place. And this structure, this great wheel, contains enormous molecular clouds.
These are the galaxy's wombs, right?
Yes, they are. Scattered throughout the Milky Way are vast, dark clouds of cold gas, the raw material for stars. These molecular clouds, composed mostly of hydrogen molecules and traces of dust, can span hundreds of light years across. Within their cold, dense interiors, gravity begins to gather material, forming clumps that collapse into new stars and planets.
And some are so large they appear as black patches against the starry sky.
They absorb visible light entirely. They are the galaxy's quiet, hidden places where the future begins in silence, tucked within curtains of shadow and gas. These processes are then violently disrupted and renewed by supernovae, which stir the galaxy like storms.
It's interesting to think of supernovae not just as destructive, but as necessary for new creation.
Absolutely. When massive stars reach the end of their lives, they explode in cataclysmic supernovae, events so powerful they can briefly outshine entire galaxies. These explosions don't just end lives, they create. The shock waves from supernovae ripple through the interstellar medium, compressing nearby clouds and triggering new waves of star formation. They also enrich the surrounding space with heavy elements like iron and gold, forged in the heart of a dying star. So they act like storms within the galactic ecosystem, stirring, fertilizing, and reshaping everything around them.
These destructive, radiant, and necessary events are part of the hidden processes of the galaxy, and much of this process, including star formation, is actually hidden from us by dust.
The Milky Way is full of light we cannot see for this very reason. Interstellar dust, made of microscopic grains of carbon, silicate, and ice, weaves through the galaxy in clouds and tendrils. In visible light, it obscures vast regions of space, blotting out stars and entire nebulae. But behind this veil, star formation continues.
So what looks like darkness is often a cradle.
Precisely. Infrared telescopes can peer through the dust, revealing glittering nurseries filled with newborn suns. The dust, though it hides, is crucial to the process, absorbing energy, helping gas cool, and shielding delicate stages of stellar birth. What seems like emptiness is often the beginning of something bright. However, not every cloud of gas becomes a star. There are starless gas clouds drifting through the galaxy.
These seem destined for collapse, but they remain dark and dormant. Why?
Some may be too diffuse, others stabilized by magnetic fields or internal turbulence. These starless clouds float through the galaxy like silent possibilities, rich in molecular hydrogen but untouched by fusion. They may one day ignite, or they may drift until torn apart by external forces, their gas recycled into other regions. In these clouds, the galaxy holds its breath, waiting for the right nudge to spark something new.
It really emphasizes the cyclical nature of the galaxy, the way it recycles matter across generations.
This is fundamental to how the galaxy functions. Stars are not permanent, they live, burn, and die. And in dying, they return their material to the galaxy. Supernovae spread heavy elements, red giants shed outer layers, and planetary nebulae drift outward into space. This enriched material then joins the interstellar medium, where it cools, condenses, and eventually forms new stars, planets, and even life.
So every atom in our bodies has passed through this cycle.
Absolutely. Born in a star, scattered into space, gathered into new form, the Milky Way is not a static stage, but a great engine of renewal. It breathes in time with its stars, making, unmaking, and beginning again. This recycling also means that metal-poor stars hold crucial clues to the early universe.
We've touched on this, but how precisely do these metals, elements heavier than helium, reveal the conditions of the early universe?
The earliest stars in the universe had almost no metals because they formed before earlier generations of stars had a chance to forge and scatter them through supernovae. Today, astronomers actively seek out these metal-poor stars, especially in the halo of the Milky Way. These faint, ancient stars preserve the chemical conditions of a time long gone. By analyzing their composition, we peer into the primordial past, into the period just after the Big Bang, before galaxies had matured.
They are indeed fossils made of light. And within this dynamic, ever-changing system, it's also true that many stars wander far from where they were born, including our own sun.
A star's birthplace doesn't always define its destiny. Over time, many stars drift away from their natal clouds, pushed by gravitational interactions, orbital resonance, or the slow pull of spiral arms. Some stars are ejected at high speeds, flung across the disk or into the halo, while others migrate gradually, shifting their orbits inward or outward. Even our sun is not where it began.
So home for a star may only be temporary.
That's a profound thought. Tracing the paths of stars reveals a Milky Way that is anything but static, a galaxy alive with movement, exchange, and quiet dislocation. This constant motion, though, might also be critical for where life can thrive. The galaxy's habitable zone, for example, may span tens of thousands of light years.
Like Earth's Goldilocks zone around the sun, not too hot, not too cold. But on a galactic scale, what defines this zone?
On a galactic scale, this region is thought to lie between the dangerous inner core, which is full of radiation and gravitational chaos, and the sparse, metal-poor outer edges where planets may be harder to form. Somewhere in between lies a wide band where conditions are stable, star density is moderate, and elements like carbon, oxygen, and iron are abundant, all crucial for life. Earth, conveniently, lies within this zone.
So this quiet orbit in a vast swirl might not be alone in finding a foothold for life, and the very spiral arms that define the galaxy's shape are not fixed structures themselves.
That's a common misconception. The Milky Way's spiral arms might seem like permanent features, grand sweeping lines carved into the galaxy's disk, but they are not made of fixed stars. Instead, they are patterns, density waves that ripple slowly through the disk, compressing gas and triggering new stars as they pass. Stars drift into these arms, shine for a while, and then drift out again.
So the spiral structure moves at a different speed than the stars themselves, like a traffic jam moving through a highway.
Exactly. From afar, it looks like form and order, but from within, it's a pattern of shifting motion held together by gravity and time, never still, always flowing. This dynamic galaxy also hums with cosmic radiation.
Beyond visible light, the galaxy has a hidden symphony of energy.
Yes, beyond visible light, the galaxy glows with more mysterious forms of energy. Cosmic rays, high-energy particles born in supernovae and distant galaxies, stream through space and pass through your body every second. X-rays and gamma rays shimmer from dying stars and black holes. Radio waves drift from gas clouds, pulsars, and the cold breath of hydrogen. These invisible hums reveal what light cannot: the violence, magnetism, and ancient fires still flickering within the galaxy's bones.
So the night sky isn't just about what we see, but this vast, hidden spectrum.
It's a hidden symphony in the dark. And within this symphony, there's even a giant gamma-ray bubble above and below the core.
The Fermi bubbles. What are these immense, ghostly lobes?
They stretch tens of thousands of light years above and below the galactic center, glowing in gamma rays. No one is entirely sure what caused them, but they may be the remnants of a long-ago outburst from the central black hole or the mark of fierce star formation that once flared through the core. These enormous structures drift silently over the galaxy, invisible to human eyes, reminding us that the Milky Way has a past we cannot fully see, echoes of violence wrapped in radiance, far above the stars we know.
And our solar system finds itself in a surprisingly quiet corner amidst all this cosmic drama. We live in a minor spur between major arms.
That's a critical detail. Our solar system doesn't lie in one of the Milky Way's grand spiral arms. Instead, we occupy a small structure called the Orion Spur, a relatively quiet lane of stars nestled between the larger Sagittarius and Perseus arms. It's not especially dense, nor especially active, but that might be precisely why we're here.
The quiet may have fostered life.
Yes, in the calm between galactic highways, massive supernovae are rarer, and radiation storms less frequent. This quiet corner may have given life on Earth the time it needed to emerge and evolve. From the outskirts, the galaxy seems dramatic and radiant, but in this quiet spur, we found just enough peace for complexity to unfold. This quiet spur also connects to the galaxy's bar-shaped center.
So, the center isn't just a bulge, but has a distinct bar structure?
When astronomers look toward the galactic core in infrared light, they see not a perfect circle, but a thick, elongated bar of stars crossing the middle, a kind of glowing bridge. This bar rotates slowly, and its gravitational pull shapes the inner spiral arms. Bars like this are common in spiral galaxies. They form when stars in the disk begin to drift inward and pile up along a central axis.
So it's not just a shape, but a dynamic engine.
Exactly. It stirs gas, triggers new stars, and feeds material toward the black hole at the center. It's part of the complexity of our galaxy's heart. And zoom out further, and the Milky Way is part of a larger structure, the local group.
We're not isolated then. We're part of a family of galaxies.
That's right. The Milky Way doesn't exist in isolation. It belongs to a collection of more than 50 galaxies known as the local group, a small cluster drifting together through space. The two largest members are the Milky Way and Andromeda, each with its own family of satellite galaxies. Scattered around them are smaller dwarfs, faint ellipticals, and star-poor galaxies made almost entirely of dark matter. The local group spans more than 10 million light-years, bound together by gravity.
So we're part of this cosmic family, linked by invisible threads of shared motion.
Yes, despite their vast separations, the galaxies of the local group are not drifting apart. Many are moving slowly toward one another. Gravity holds them in a kind of slow-motion ballet. Over time, this group may condense, galaxies may merge, fade, or be absorbed. It's not a static arrangement, but a gentle gathering of cosmic islands.
And the Milky Way's disk itself has layers, a thick and thin component.
Indeed, the Milky Way's disk looks flat from a distance, but up close, it's clearly layered. We live in the thin disk, a wide, dense plane filled with young stars, open clusters, and star-forming gas. But above and below it lies the thick disk, which is older, puffier, and more diffuse. Stars in the thick disk tend to be older, with fewer heavy elements.
So these layers tell us about different eras of star formation.
Precisely. Their orbits are more tilted and elliptical, suggesting they formed under different conditions or were stirred by early galactic collisions. The galaxy's disk is textured, layered, and shaped by time, like sediment settled on the floor of a cosmic ocean. And threading through this complex disk is the galaxy's magnetic field.
Invisible to the eye, yet pervasive.
It's a vast magnetic field stretching across the disk, rising into the halo and weaving through the interstellar medium. Though weak by earthly standards over galactic distances, it shapes how cosmic rays travel, how gas clouds collapse, and how matter flows through space. It aligns with spiral arms, forms arcs above the plane, and twists into loops that defy simple explanation. The Milky Way doesn't just glow with light, it breathes with magnetism.
A subtle pulse running through its bones. And within all this, interstellar space isn't empty, it's a turbulent sea.
Absolutely. The interstellar medium, that thin blend of gas, dust, and plasma between the stars, is constantly stirred by shock waves, magnetic fields, and the motion of stars. Temperature can vary wildly, flows of material collide, mix, and fragment. On large scales, this creates a kind of turbulence, like a slow-motion ocean swirling through the disk. Star formation, cosmic rays, and even galactic evolution are all affected by this restless sea.
So what looks from afar like calm starlight is, up close, a dynamic, rippling fabric. And through this fabric, cosmic rays constantly pass through us from the galaxy.
Every second, high-energy particles, mostly protons and atomic nuclei, stream through your body, launched long ago by exploding stars. These are cosmic rays, and they are everywhere. They travel close to the speed of light, bending through magnetic fields, bouncing off clouds, and occasionally colliding with atoms in Earth's atmosphere. Most of the time, we don't notice them, but they carry stories from across the galaxy, evidence of ancient supernovae, traces of distant acceleration, messages from the violent hearts of stars.
So even as we rest, the galaxy is whispering in particles, and it's whispering in a way that suggests the galaxy isn't perfectly symmetrical.
Though many diagrams show it as a neat, even spiral, the Milky Way is subtly lopsided. One side of the disk appears thicker. Some spiral arms are brighter, longer, or more curved than others. Even the stellar halo is slightly off-center. These asymmetries may be caused by gravitational encounters, past mergers, or the influence of dark matter. They remind us that galaxies, like living things, carry traces of their histories in their shapes. Scars of collisions, wrinkles of time, and quirks of uneven growth that give them character and depth.
A graceful imbalance, then, and high above the galactic plane, drifting through the halo, the oldest known star may reside.
Indeed, astronomers have discovered a star there that may be nearly as old as the universe itself. It contains almost no heavy elements, a signature of stars born soon after the Big Bang, before generations of supernovae enriched the cosmos. It likely formed over 13 billion years ago, long before the Milky Way was fully formed. It burns quietly now, a low-mass star, but it is rich in history.
A time capsule, a living relic from the universe's earliest dawn, and within the more populated regions, the center of the galaxy spins faster than the outskirts.
In the inner regions of the Milky Way, stars orbit the center much more rapidly than those farther out. Near the core, the gravitational pull is stronger, packed with mass from stars, dust, and the supermassive black hole Sagittarius A. This causes stars to sweep through tighter, faster orbits, completing revolutions in just a few million years. Out in the suburbs of the galaxy, like where our sun lives, stars orbit more slowly, taking hundreds of millions of years.
This uneven rotation creates twisting patterns and stretches the spiral arms. It implies the galaxy moves like a great wheel, but one whose rim lags behind its core.
Exactly, and those spiral arms themselves are shaped by density waves, not fixed structures, as we discussed. It's like a traffic jam. Cars move into the jam, slow down, then speed up as they leave, but the jam itself persists. Stars do the same in the spiral arms. They move into denser regions, compress, trigger star formation, and then eventually move out. This creates a self-sustaining illusion of structure.
So from afar, they appear still, but from within, they are a dance of matter and rhythm. And all this begins from the simplest ingredients. Stars are born from cold, collapsing gas.
In the dark arms of the Milky Way, star formation begins in silence. Massive clouds of molecular hydrogen, sometimes hundreds of light years wide, drift through space, chilled to just a few degrees above absolute zero. Within these clouds, gravity slowly takes hold. Small regions grow denser and begin to collapse under their own weight. As the gas falls inward, it heats, spins, and flattens, forming a protostar at the center.
Until nuclear fusion ignites, and a new star is born. From the coldest shadows come the brightest lights.
Spun gently into being by the quiet force of gravity, but many stars don't remain in their birth clusters. Star clusters can dissolve into the galactic field.
So stars aren't born in isolation, but in groups, and then scatter over time.
That's right. These clusters, bound by mutual gravity, drift together for millions or even billions of years. But over time, tidal forces from the Milky Way's mass, close encounters with other stars, and internal dynamics all work to pull clusters apart. Stars peel away one by one until the cluster fades into the general star field of the galaxy. Even our sun was born in a stellar cluster long ago. Its siblings are now scattered, dimmed, or lost.
It's a reminder that even for stars, home is temporary, and within this scattering, astronomers find ancient hypermetal-poor stars.
These are among the rarest and most precious objects in the Milky Way. Their atmospheres contain almost no elements heavier than helium, sometimes less than 100,000th the iron found in the Sun. They are believed to be among the first stars born after the very first supernovae, carrying only faint traces of enrichment from a universe still forming itself. They're incredibly old, incredibly pure, and scattered in the halo like distant lanterns from the dawn of time. Each one is a glowing, gravitationally bound signature from a near-forgotten epoch.
They truly are relics, and throughout all this, planetary systems form throughout the Milky Way, meaning planets are not a rare feature of the cosmos.
They're a natural consequence of star formation. As a new star ignites, a rotating disk of leftover gas and dust surrounds it. Within this disk, particles stick together, gather mass, and grow into worlds. Across the Milky Way, planetary systems are common. Some are vast, with gas giants and frozen moons. Others are compact, with rocky planets hugging close to dim stars. The galaxy isn't just full of stars, it's full of systems, each with its own unique balance and potential.
And our own Earth is in a particularly stable spot, near the co-rotation radius.
Yes, this is a special distance from the galactic center where the average speed of stars matches the rotation speed of the spiral arms themselves. Our Sun orbits close to this boundary. This gentle match in motion may help us avoid frequent crossings of spiral arms, which are places with higher star density, more supernovae, and gravitational disturbances. We live, quite possibly, in a more stable neighborhood of the galaxy, shielded not by walls, but by resonance.
A quiet place for life to evolve, but even in this stable orbit, the Sun bobs up and down through the galactic plane.
As it orbits the Milky Way, the Sun doesn't follow a perfectly flat path. Instead, it moves in a gentle wave, drifting above and below the galactic plane like a cork in slow motion, rising and falling over tens of millions of years. This vertical oscillation is caused by the gravitational tug of the galaxy's mass. Some researchers have even wondered if this motion might influence cycles of extinction on Earth, though the evidence isn't clear yet. Still, it's a reminder that even on its steady path, the Sun is swaying softly through space.
It adds another layer of subtle, immense motion. And underpinning all of this, holding the galaxy together, is dark matter, which we still don't understand.
It's one of the greatest mysteries in science. Dark matter makes up most of the Milky Way's mass, yet it has never been seen directly. It doesn't emit or absorb light, it passes through ordinary matter as if it weren't there. But its gravitational effects are unmistakable. It holds the galaxy together, explains the unexpected rotation speeds of stars, and shapes the formation of large-scale cosmic structures. We detect it not by seeing it, but by watching how it moves other things. It is the galaxy's hidden scaffolding, invisible, silent, and still one of the greatest unknowns.
And the implications of this are that there's more mass outside the disk than inside.
Absolutely. Most of the Milky Way's visible stars lie within the flat, luminous disk, but the majority of its mass resides in that enormous dark matter halo extending far beyond the furthest stars. This halo holds the galaxy together, outweighing the disk by a large margin. When we picture the Milky Way, we often focus on its spiral arms, but that's only the glowing surface. The true bulk, its gravity and motion, is mostly hidden, enveloping everything like a quiet shroud.
And our galaxy's core, currently quiet, may have flared as a quasar in the past.
That's a fascinating theory, supported by evidence like the Fermi bubbles we discussed earlier, and traces of high-energy light reflected in surrounding clouds. These suggest that Sagittarius A may have once flared as a quasar, a brilliant, violent beacon fueled by infalling matter, capable of outshining entire galaxies. If the Milky Way once burned like this, it would have looked dramatically different, a spiral wrapped around a blinding heart of light. That time has passed, but the echoes remain.
So the galaxy's structure is constantly changing over billions of years, not just visually, but in its very energetic core.
Precisely. Galaxies may look timeless, but they are always evolving. Spiral arms shift, bars form and dissolve, gas flows inward and outward. Stars are born and die, leaving behind a changing population. Even the shape of the Milky Way's disk, warped, rippling, and lopsided, is slowly altering. Encounters with dwarf galaxies and dark matter can bend or twist the structure. The Milky Way of today is not the one that was, and not the one that will be. Its beauty lies not in permanence, but in quiet transformation. And part of this transformation comes from external forces, like gravitational waves rippling through the galaxy from distant mergers.
Ripples in the fabric of space-time itself. How do we detect something so subtle within our own galaxy?
All across the universe, massive objects collide. Black holes spiral together, neutron stars crash, and entire galaxies merge. These events send out gravitational waves, and though incredibly faint, some of these waves pass through the Milky Way, distorting space by tiny amounts as they travel. Observatories like LIGO and Virgo have already captured several. New experiments aim to detect the background hum of gravitational waves that fills the cosmos. Even now, space itself is subtly shifting, a testament to the universe's ongoing evolution.
It's profound to think that even our own galaxy is being subtly influenced by events happening light years away. This dynamic nature also leads to some stars orbiting in elongated, tilted paths.
Not all stars move in neat circles around the galactic center. Some follow long, stretched ellipses, their paths looping high above and far below the disk, tilted at odd angles from the main plane. These stars likely come from different origins, relics of dwarf galaxies swallowed by the Milky Way, or survivors of ancient gravitational upheavals. Their orbits are like three-dimensional maps of the galaxy's chaotic past. By tracing their motion, astronomers reconstruct the invisible architecture of the Milky Way's mass and memory. They drift like messengers from disrupted systems.
Messages from the galaxy's past. And then there are the particles we can barely detect, neutrinos.
Every second, trillions of neutrinos pass through your body, straight from the stars. These ghostly particles are produced in nuclear reactions, from the sun, from supernovae, and from cosmic rays striking atoms in space. The Milky Way is bathed in them, yet they are so light, so unreactive, that they slip through almost everything, leaving no trace. Special observatories buried deep underground or under ice try to catch just a few, flashes of light from a rare collision. Neutrinos carry information from places we cannot see, stellar cores, collapsing giants, and the galaxy's unseen energy. They are the whispers of cosmic fire.
So the galaxy is communicating with us, even if we can barely perceive it. And interstellar space, far from being empty, is a turbulent sea.
That's a crucial understanding. The thin clouds of gas, dust, and plasma between the stars are constantly stirred by shockwaves, magnetic fields, and the motion of stars. Temperature can vary wildly. Flows of material collide, mix, and fragment. On large scales, this creates a kind of turbulence, like a slow-motion ocean swirling through the disk. Star formation, cosmic rays, and even galactic evolution are all affected by this restless sea. What looks from afar like calm starlight is, up close, a dynamic, rippling fabric shaped by invisible winds and ancient energy.
And within this turbulent sea, the galactic halo may contain rogue planets.
Planets are not always tethered to stars. Some form normally and are later ejected from their systems. Others may never have had a star at all. These are rogue planets, worlds adrift in the galaxy, cold, dark, and alone. Though difficult to detect, studies suggest there may be billions of them in the Milky Way, some even in the outer halo, where stars are few and far between. Without light or warmth, they float unseen, warmed only by internal heat. Orphans of the galaxy, planetary drifters following long, lonely paths through the darkness between stars.
It's a lonely thought. And magnetic fields also play a role, shaping the flow of cosmic dust.
Interstellar dust moves not just under gravity, but also under the influence of the galaxy's magnetic field. These fields thread through the Milky Way like invisible currents, guiding the motion of charged particles and influencing how gas and dust align. In some regions, dust grains spin rapidly, emitting faint microwave light. In others, they align with magnetic lines, polarizing the starlight that passes through them. Dust is not passive. It dances to a magnetic rhythm, leaving hidden patterns in the dark.
It's a hidden layer of complexity. And speaking of elements, some stars are enriched by neutron-star collisions.
When two neutron stars spiral together and collide, they create one of the most violent events in the universe, a kilonova. In this brief, blinding explosion, enormous quantities of heavy elements are forged: gold, platinum, uranium, and more. These materials are cast into space, mixing with gas and eventually forming new stars. Some stars in the Milky Way carry the chemical fingerprints of these rare events, enriched in elements that could only have come from such collisions. They are not just luminous bodies, but record keepers of ancient cataclysms, burning with the residue of stellar wreckage and cosmic alchemy.
These are rare but profound events shaping the very building blocks of stars. And speaking of hidden structures, the Milky Way may even have a hidden bar within a bar.
At the heart of the galaxy, we know there's a bar of stars, that elongated bridge. But deep within that bar, astronomers have found hints of another, smaller bar, tilted at a different angle and rotating independently. This inner structure is difficult to see directly, obscured by dust and distance, but its gravitational influence appears in the motion of nearby stars and gas. These bars help funnel material toward the supermassive black hole, feeding it and shaping the dynamics of the core. The Milky Way's center is not one simple shape. It's a layered, shifting labyrinth of light and motion.
A galaxy's complexity just keeps unfolding, and despite its vastness, it's not a closed system. Gas inflows feed the galaxy from the cosmic web.
The Milky Way draws in fresh gas from the intergalactic medium, long, tenuous streams flowing through the vast cosmic web. These inflows provide the raw material for new stars, replenishing what the galaxy loses over time. Some gas arrives as cold filaments, slipping quietly into the disk. Other streams fall in hotter, shock-heated forms, lighting up in ultraviolet or X-ray light. These invisible rivers sustain the galaxy's growth and evolution, linking it to the larger universe beyond. Even now, the Milky Way drinks from distant reservoirs, nourished by threads of matter spun from the early cosmos.
So the galaxy is constantly interacting with its environment, and within the disk, hot gas bubbles form chimneys out of the disk.
When clusters of massive stars go supernova, they create enormous cavities in the interstellar medium. These can join together into superbubbles, vast pockets of hot gas that punch upward through the galactic disk and vent into the halo. The result is a kind of chimney, a channel where energy, gas, and magnetic fields escape from the plane of the galaxy. These chimneys regulate the pressure of the interstellar medium, redistribute metals, and help shape the halo structure. The galaxy, in this way, breathes not just within the disk, but through towering columns that carry its energy up and out into the dark.
It's a powerful image of the galaxy's internal respiration, and when we look at the Milky Way beyond visible light, it shines in X-rays from old stars and black holes.
Though the Milky Way appears calm in visible light, it glows fiercely in other wavelengths. X-rays pour from its core, from collapsed stars, and from the edges of black holes. White dwarfs and neutron stars in binary systems can siphon matter from companions, heating it to millions of degrees. Hot gas in the halo also emits faint X-rays, revealing the galaxy's larger skeleton. We cannot see this high-energy light with our eyes, but telescopes like Chandra and XMM Newton paint a very different portrait of the galaxy, not a tranquil spiral, but a realm of extreme temperatures, compact remnants, and hidden radiation.
It truly reveals a hidden intensity, and within this intense environment, pulsars act as cosmic clocks throughout the Milky Way.
When a massive star dies and collapses into a neutron star, it may be left spinning, fast and precise, with beams of radiation sweeping across space. These are pulsars, and some rotate hundreds of times per second, pulsing in regular, measurable rhythms. They are so consistent that astronomers use them as cosmic timekeepers, tracking their signals to measure distances, test gravity, and even search for gravitational waves. Across the Milky Way, pulsars blink quietly, remnants of death, but also beacons of astonishing order. They keep time not for minutes or days, but for entire epochs.
Ticking steadily in the silence between stars. And just as X-rays reveal a hidden intensity, radio waves map the hidden structure of the galaxy.
Much of the Milky Way is invisible in visible light, hidden by dust, distance, or faintness. But radio waves can slip through these barriers, revealing structures otherwise unseen. They trace cold hydrogen gas, outline magnetic fields, and highlight emissions from pulsars, supernova remnants, and even distant quasars beyond the galaxy. Using arrays of radio telescopes, astronomers have mapped the spiral arms, measured the warp of the disk, and discovered star-forming regions cloaked in darkness. Where light is blocked, radio soundings let us see. The galaxy speaks in a language we can't hear, but one that science has learned to translate into shape and shadow.
It's like having a new sense to perceive the galaxy, and our sun, this star that hosts our solar system, was likely born in a stellar cluster.
Stars rarely form in solitude. They're usually born in groups, stellar clusters shaped from the same collapsing cloud of gas and dust. Our sun was almost certainly one of these. Long ago, it shared space with hundreds, perhaps thousands of sibling stars, all born in the same cradle. Over time, gravitational tides, passing stars, and the motion of the galaxy scattered the cluster. Most of the sun's siblings have wandered far, flung into different orbits, carrying with them fragments of our shared past. Some may still shine nearby, invisible among the stars, lost family in a sea of light.
And astronomers are actively searching for those scattered siblings of the sun.
Yes, using vast surveys like Gaia and spectroscopic databases, researchers hope to identify these long-lost relatives, stars that share our sun's age, motion, and chemical fingerprint. A few candidates have emerged, and if found, they could reveal details about the conditions in which the sun and the early solar system were born. It reminds us that our place in the galaxy is not entirely solitary. Somewhere out there, the sun's ancient kin may still shine.
A beautiful thought. And speaking of our galaxy's subtle movements, the galactic disk wobbles as it spins.
The Milky Way's disk is not perfectly flat. It wobbles gently, rippling like a spinning plate nudged off balance. This warp is most visible in the outer regions, where the disk bends upward on one side and downward on the other. It may be caused by the gravitational influence of nearby dwarf galaxies, interactions with dark matter, or internal asymmetries. The wobble rotates slowly, like a vast wave moving through the stars. From Earth, we don't feel it, but from afar, the Milky Way is a breathing, undulating sheet of stars, curving gently as it turns.
And this grand motion also exerts tidal forces. Galactic tides can distort star clusters and streams.
Just as the moon's gravity pulls tides on Earth, the immense mass of the Milky Way exerts tidal forces on everything within it. Star clusters, satellite galaxies, and even globular groups feel the galaxy's uneven gravitational pull. Over time, these tides can stretch and distort them, drawing out long stellar streams or peeling stars away from their orbits. Many of the faint arcs of stars mapped across the sky are remnants of such encounters, clusters in the process of being unraveled, galaxies slowly torn apart. The galaxy doesn't break these structures suddenly, it unravels them patiently, strand by strand, over millions of years.
It's a subtle form of cosmic destruction and reshaping. And despite all our observations and measurements, the Milky Way's mass is still uncertain.
You might think we would know the mass of our own galaxy, but measuring it is remarkably difficult. Stars and gas make up only a small portion of the total. The rest lies in the vast dark matter halo, which we cannot see directly. Estimates vary. Some suggest a mass close to 1 trillion times that of the Sun. Others place it much higher. The uncertainty comes from trying to measure how fast stars orbit at great distances, a task clouded by limited data and the influence of invisible matter. The Milky Way is our home, but its weight remains a quiet mystery.
And this uncertainty even impacts our understanding of its relationship with Andromeda. For many years, it was assumed Andromeda was more massive than the Milky Way, but that may not be the case.
That's right. Recent measurements suggest that the Milky Way's dark matter halo may be broader and denser than previously believed. If that's true, our galaxy could actually outweigh Andromeda, despite its more modest visible appearance. This matters not only for comparisons, but for predictions. When the two galaxies eventually merge, their relative masses will shape the encounter's dynamics. The Milky Way may look gentle, but beneath its quiet spiral arms, it carries more weight than we once imagined.
It adds a fascinating twist to our future cosmic collision. And speaking of interactions, the Magellanic Clouds, those two bright satellite galaxies, may be on their first orbit around the Milky Way.
Long thought to be long-standing companions, new evidence suggests they might be newcomers, captured only recently in cosmic terms. Their velocity and motion through space hint that this could be their first close pass. If true, their arrival has stirred the outer disk and warped the galaxy's shape, as if the Milky Way is responding to a new gravitational guest. The quiet sky is full of first encounters.
And trailing behind them is the Magellanic Stream, a ribbon of stripped gas.
It's a vast ribbon of hydrogen gas stretching over hundreds of thousands of light years, wrapped in curves and arcs across the southern sky. This stream was pulled away by tidal forces as the dwarf galaxies passed close to one another and to the Milky Way. Invisible light, it reveals itself in radio wavelengths, a long, trailing whisper of motion and loss. The stream may one day feed new star formation in the Milky Way or settle into the halo like a thread of memory stretching between galaxies.
A tangible sign of ongoing galactic interaction, and not all gas follows the main disk's plane. Some gas clouds orbit in polar directions.
Yes, some clouds of gas and even some stars move in highly inclined orbits, passing high above and far below the galaxy's main structure. These polar orbits likely come from past mergers, when dwarf galaxies or stray clouds were captured at odd angles. They continue to orbit on tilted paths like comets around a planet. These misaligned orbits are records of disruption, visible reminders that the galaxy is not a closed system, but an evolving structure shaped by the unpredictable flow of cosmic history.
They're like historical markers, and speaking of dramatic events, giant shells of gas surround past starbursts.
In several regions of the Milky Way, astronomers have found enormous spherical shells of gas, some spanning hundreds of light years. These shells are the remnants of powerful starbursts, episodes when clusters of massive stars formed together, lived brief lives, and exploded in rapid succession. Their combined winds and supernovae carved out huge cavities, blowing gas outward in all directions. Over time, the expansion slows, but the shells remain, ghostly bubbles marking where the galaxy once burned bright with stellar birth and death. These are the fossils of cosmic fireworks.
Still echoing in the cold. And though space is vast, stars occasionally collide in dense regions.
It's true that space is vast and stars are small, but in the densest regions of the Milky Way, such as the cores of globular clusters, stars can pass close enough to interact and even collide. When they do, the result can be dramatic. A burst of light, the merging of two suns, or the formation of a rare blue straggler star, one that appears younger than its neighbors. These collisions are rare, but over billions of years, the tightest stellar neighborhoods can rearrange themselves through gravity and chance. In these crowded stellar cities, time moves differently.
And even binary stars, systems of two stars orbiting each other, can be torn apart by tidal forces.
Many stars live in pairs, orbiting each other in gravitational embrace, but even this bond can be broken. If a binary system passes close to the Milky Way's central black hole or through a dense cluster, tidal forces can disrupt their orbit, flinging one star away while the other is captured or slowed. In some cases, a companion is hurled out of the galaxy entirely, becoming a rogue star speeding through intergalactic space. These stellar breakups happen silently, a quiet tearing of ancient partnerships by gravity's indifferent hand.
So some stars escape the galaxy entirely, becoming solitary pilgrims.
That's right. Most stars are gravitationally bound to the Milky Way, but occasionally a star reaches escape velocity over 500 kilometers per second and is flung outward, never to return. These hypervelocity stars are rare but real. They carry the galaxy's memory outward, becoming solitary pilgrims in the great dark between galaxies. And conversely, the Milky Way contains stars from other galaxies.
So we have stars leaving and stars joining.
Exactly. Not all stars within the Milky Way were born here. Some may have originated in other galaxies, captured during mergers, or flung into our halo from distant regions of the local group. These intergalactic wanderers often move on unusual orbits far from the disk, tracing paths through the outskirts or halo. They can be identified by their composition or motion, stars that don't quite fit the local patterns. Like cosmic immigrants, they bring stories from other environments, other histories, other skies. The Milky Way is not a sealed system, it is a living mosaic, slowly stitched together by time and motion.
It's a beautiful metaphor. And within this mosaic, a fountain of gas cycles between the disk and halo.
Above and below the Milky Way's bright disk, gas rises and falls in a quiet loop known as the galactic fountain. Supernovae and stellar winds heat and eject material upward into the halo, where it cools, condenses, and gently rains back down over millions of years. This cycle stirs the interstellar medium, redistributes heavy elements, and helps regulate star formation. It's a quiet respiration, a breathing motion of matter between the dense plane and the vast halo. The galaxy, in this way, doesn't just spin, it circulates. It exhales and inhales, keeping its structure in motion across immense spans of time.
It's an incredibly interconnected system, and within the galaxy's dust grains, there are organic compounds.
Within the clouds of interstellar dust that drift between stars, scientists have detected complex organic molecules, carbon-based compounds that form the raw ingredients for life. These include polycyclic aromatic hydrocarbons, simple sugars, alcohols, and more. Though not alive, they are chemically rich, formed in the atmospheres of dying stars or within cold clouds shaped by radiation. These tiny grains, carried across light years by galactic winds, settle into the gas that forms stars and planets. Some may have fallen onto the early Earth. The galaxy's dust is not just debris, it is a cargo of potential, drifting silently through the dark.
So interstellar clouds may seed solar systems with ingredients for life.
The birthplaces of stars are also the birthplaces of worlds. As planetary systems form from collapsing clouds of gas and dust, they inherit the chemical fingerprints of their parent nebula. If that cloud contains water, carbon compounds, and other building blocks of biology, those ingredients may end up in comets, asteroids, or planets. Some regions of the Milky Way are especially rich in such prebiotic chemistry. We don't yet know how common life is, but the conditions for it seem to arise naturally. The seeds of life may be scattered far and wide, tucked into the galaxy's coldest cradles, waiting for a place to grow.
A truly profound implication. And some stars spin much, much faster than our sun, rotating hundreds of times faster.
Most stars spin, but some spin incredibly fast, completing a full rotation in just a few hours. These rapid rotators are often young, massive, and unstable, with equators that bulge from centrifugal force. A few reach such high speeds that they fling off material, forming glowing disks around themselves. Our sun rotates once every 25 to 35 days, depending on latitude. But these fast-spinning stars rotate hundreds of times more quickly, approaching physical limits. Their internal structures and evolutionary paths are different. Their lives may be brief, but while they last, they spin like sirens in the dark.
And our entire solar system is tilted relative to the galactic plane.
From Earth, the Milky Way arcs across the night sky in a graceful band of light, but it doesn't align with the plane of our solar system. The galactic plane, the flat disk in which most of the galaxy's stars reside, is tilted about 60 degrees relative to the ecliptic, the path traced by the sun and planets. This tilt is why the Milky Way rises at an angle and why it shifts position with the seasons. We are part of the galaxy, but our own little system is angled slightly askew, a small, tilted boat drifting through a larger spinning sea of stars.
It adds to the complexity of our cosmic address, and some stellar remnants are even older than the galaxy's disk itself.
Among the faint stars in the halo, astronomers have found white dwarfs, the cooling cores of once luminous stars, that are older than the Milky Way's thin disk itself. These ancient remnants formed when the galaxy was young, before its main structure had fully settled. Their existence hints at an earlier time of star formation, a deeper history etched into the outer halo. They have burned for billions of years, slowly fading, carrying with them the quiet residue of a time when the Milky Way was still gathering its shape. The disk may be bright, but the halo remembers further back.
It's like finding deep history, and the farthest stars orbit well beyond the main structure, giving us a sense of the galaxy's true extent.
The Milky Way's most distant stars orbit far beyond the familiar spiral arms, tens or even hundreds of thousands of light-years from the center. These stars move through the galactic halo on slow, wide paths, taking billions of years to complete a single orbit. Many were likely captured from smaller galaxies in past mergers, now drifting in the outermost reaches like distant sentinels. They are faint, sparse, and far between, but they help define the galaxy's size, shape, and gravitational influence. The Milky Way is not just what we see, it extends deep into the dark, shaped by wanderers at its edge.
And this grand, complex structure is also subtly lopsided in several ways.
Though often pictured as a symmetric spiral, the Milky Way is subtly lopsided. One side of the disk is thicker than the other. The spiral arms are uneven in brightness and extent. Even the stellar halo is slightly off-center. These asymmetries likely arise from gravitational interactions with the Magellanic Clouds, with dark matter clumps, or with past mergers. The galaxy is not a perfect pinwheel. It is a living structure, marked by tugs and twists, like a spinning dancer whose skirt has been caught by the wind. Its beauty lies in that irregularity, a graceful imbalance sculpted by time.
It paints a picture of constant, subtle adjustments. To understand all of this, astronomers rely on specific tools, and one of them is mapping the galaxy using variable stars.
Certain stars pulse in brightness over regular intervals, expanding and contracting like slow, luminous heartbeats. These are variable stars, and some types, like Cepheids and RR Lyrae, have well-known relationships between their true brightness and their pulse period. By measuring how long a star takes to brighten and dim, astronomers can determine its true luminosity, and by comparing that to how bright it appears, its distance. These stars serve as cosmic yardsticks, helping us map the shape, structure, and scale of the Milky Way. They are lights that measure the dark, blinking beacons scattered through the spiral.
It's a clever way to measure immense distances, and all this data is being revolutionized by the Gaia mission.
Launched by the European Space Agency, the Gaia spacecraft is creating the most precise map of the Milky Way ever made. By measuring the positions, motions, and brightness of over 2 billion stars, Gaia reveals the galaxy's three-dimensional structure and its motion through time. It has uncovered streams from shredded galaxies, mapped the warp of the disk, and traced the sun's orbit with exquisite detail. With each new data release, Gaia deepens our understanding, turning a hazy smear of stars into a sharp, living map. It is astronomy's most ambitious star chart, a quiet revolution unfolding among the stars.
A revolution allowing us to truly see our galactic home. When we look up on a dark night, that hazy river of starlight across the sky is the galactic plane, marking a dense path of stars.
That's the thickest slice of the Milky Way's disk. It's not just a line, but a depth, a vast, flattened band where the majority of the galaxy's stars reside. Through this plane, stars are densely packed, dust is layered, and star formation is common. From our vantage point, we're looking along the grain of the galaxy, peering through its richest corridors. This band isn't just beautiful, it's the crowded, humming heart of where most stars live and die.
And the night sky is brightest toward the galactic center, even if we can't see the very core.
The core of the Milky Way lies in the direction of the constellation Sagittarius, a rich, glowing concentration of stars, dust, and unseen mass. From Earth, we can't see the very center in visible light because dust clouds obscure our view, but the area glows with brightness in infrared and radio. Even with the naked eye, the region appears more crowded, more luminous, filled with the overlapping light of billions of stars. We orbit far from the center, in a quiet suburb of the galactic disk, but when we look inward, we glimpse the crowded city at the galaxy's heart.
And all this leads to the fundamental truth that we see the Milky Way edge on from Earth.
Because we live within it, we cannot look down on the Milky Way from above. Instead, we see it from the inside, a flat ribbon of stars stretching across the sky, curved only by the horizon. This edge-on view compresses the galaxy into a single arc, making it hard to grasp its full structure from our perspective. It took centuries of observation, cataloging, and mathematical deduction to realize the spiral we belong to. From Earth, we gaze through its disk like standing in a forest and looking along the line of the trees. We do not see the shape we're part of, only the vastness that surrounds us.
The Milky Way holds far more than we can ever possibly see, Lily. It's truly a universe within a universe, isn't it?
It is, James. Even with our most sensitive instruments, we glimpse only a fraction of what the Milky Way contains. Light is blocked by dust. Motion is hidden in silence. Dark matter outnumbers luminous stars. Between every star lies emptiness, and within every empty space, potential. The Milky Way is not just what we see, it is what we suspect, what we infer, what we long to understand. It holds ancient light, future stars, drifting worlds, and questions still without answers. And within that vastness, somehow we find ourselves, one planet among many, orbiting a quiet star, floating through a story too wide for the eye.
The Milky Way is a dynamic, interconnected system, far more intricate and alive than we can often perceive. It's a constant dance of creation and destruction, growth and transformation, all held together by invisible forces. Its story is our story.
Indeed, every atom in our bodies traces its lineage to the earliest times, born from the same matter that now fuels suns and whispers through clouds of interstellar dust. We are participants in its long and luminous unfolding.
If this exploration of the Milky Way has sparked your curiosity, consider sharing this episode with someone who might also appreciate a deeper look at our cosmic home.